Welcome to my short introduction to InterACt, a tool for unit test-based integration testing. My name is Niels Wild. I'm with the research group Software Construction at RWTH Aachen University, and I'm the author of the tool. Before I introduce the tool itself, I would like to introduce the ideas and concepts behind InterACt. Whenever we develop software, we use some kind of software development lifecycle. We start with requirements, design decisions, and we create the actual implementation based on these decisions. We then test the implementation to make sure that the requirements are fulfilled. We also have deployment and maintenance phases, but we don't care about those today. So starting with the documented specification that is a result of the requirements analysis and the design decisions, we create the actual components implementation. These implementations are the actual specifications of the components that are tested with the unit test cases. These unit test cases should make sure that the actual specification complies with the documented specification in the beginning. However, these unit tests are also interpretations of the documented specification, so we really make sure that the actual specification complies with our interpretation of the specification. This becomes a problem if multiple components interact with each other. In this case, a component A provides some interface to other components, in this case component B. They were both developed with the same documented specification in mind, but the actual specification provided by component A of the interface might not comply with the expected specification provided by component B of that interface. The expected specification of component B describes how component B intends to use the actual interface that is provided by component A. Many studies show that misinterpretations of the documented specification that lead to different implementations are one of the main causes for faults in software systems. So that's why we do integration testing. We want to make sure that the actual specification complies with the expected specification of those components that use our interfaces, or if there are any errors or faults that we need to correct. So that brings me to the automated iterative integration testing process based on unit test cases that I would like to introduce next. Therefore, we introduce the unit test-based interaction meta model that contains information about the components and their behavior. On the one hand, we have the static information about the component, the interfaces they provide, and we distinguish these interfaces between outgoing and incoming interfaces that are bound to each other. On the other hand, we also have test information about the abstract test cases that test the components, the concrete test cases that are derived from the abstract test cases by providing actual values, and the messages that we observed during test execution that were sent to and received by the components' interfaces. We distinguish three different types of messages: stimulus messages that are received by the component under test and that trigger some kind of behavior, component responses that are triggered by the component under test as a response to the stimulus, and the environment responses that are usually provided by mocks during unit testing that are a response to the component responses that were sent by the component under test. So let's take a look at a concrete unit test. In this case, the unit under test receives a stimulus message on the first interface. Due to this stimulus, the component reacts with a component response on the second interface that is sent to the environment mock. This environment mock responds with another environment response message on the third interface as a reaction to that component response. All these messages are captured and stored in the model that I showed before. So looking at the model, and after mining the outgoing and incoming interfaces based on the protocol specifications, we can already detect certain kinds of integration faults. In this case, interpretation faults, which means we can detect missing function faults and extra function faults. So if some outgoing interface is not bound to an incoming interface, we do have some missing function fault as there's no component that can receive the messages we send on this outgoing interface and probably react in the way that we expect the environment to react to that message. For extra function faults, it's the other way around. So if there are any incoming interfaces that are not bound to outgoing interfaces, we provide some functionality that is not used by any other component. Of course, it could also be that there are just no test cases that trigger these interfaces or messages on these interfaces. So we have test gaps and we do not have the information about these components in our model captured. Of course, this is only possible for private interfaces. Public interfaces that are used by third parties might not be used in our unit test cases, so we do not have the information in order to create this binding between outgoing interfaces and incoming interfaces of components that use the functionality. So taking another look at the unit test, we can also see that it incorporates the expected specification of the interaction with the environment. In fact, the expected specification here is that when a message like M2 is sent to the environment via interface 2, a message like M3 is expected as a response with respect to the unit test's expectations on the third interface. So let's take a look at the unit test of another component. In this case, the component receives a stimulus message on the fourth interface and responds with a component response on the fifth interface. This information is also captured. It represents the behavior that is tested by the unit test, the actual specification. So when a message like M4 with respect to the unit's behavior is received, a message like M5 is sent with respect to the unit test's expectations. We can use this information in conjunction with the information about the bound interfaces to create integration test cases. In this case, interface 2 is bound to interface 4 and interface 5 is bound to interface 3. This way we can create the actual integration test case by replacing the stimulus message in the unit test case of the second component with the component response that was captured during unit test execution of the first component. We call this the interaction test case. Furthermore, we can capture the component response that is then captured on interface 5 and use this as a replacement of the mocked response in the unit test case of the first component to create another interaction test case. The combination of the unit tests and the interaction tests actually tests the integration between those two components. Thus, we can detect interpretation faults, miscoded call faults, and interface faults, as the components might not be able to process the messages that they now receive, as these messages are no longer the messages that were defined by the team that developed the component in the unit test cases, but are the messages that are actually triggered by the components under test in the other test cases. It also has the benefit that these interaction test cases are just as resource intensive as the unit tests themselves. In contrast to standard integration testing, we do not need any resource intensive integration environment. So how does InterACt realize this testing process? So let's take a look at the architecture. As you can see, InterACt provides interface observers that are protocol specific and also implementation specific. These interface observers observe the messages that are sent to and sent from the component under test during unit test execution. This information is stored in the UDBI model store, and the interface binders that have to be provided for each protocol ensure that the interfaces that need to be bound to each other are bound to each other. The interaction test case generator then extracts the expectations of each component towards their environment from these models and generates new parameters that are provided to the unit test case harnesses in order to test the interaction between a component and its environment. This information is then again stored in the UDBI model in order to validate that the expectations of each component are validated and fulfilled by the behavior of other components. So let's take a look at a concrete example that is also provided via GitHub. There we have a user that is sending a transfer request to some money transfer component. This money transfer component then sends the IBAN to an IBAN validator that ensures that the IBAN has a concrete format, a valid format, and forwards this IBAN to the blacklist checker that ensures that the target IBAN is not on the blacklist and thus the actual transfer is allowed. The validation result is passed back to the IBAN validator and passed back to the money transfer component that then tells the user whether its transfer request was successful or not. So let's see how this is implemented using InterACt and the InterACt JUnit extension. So first of all, we will start the InterACt server. It is responsible for capturing all the information that was observed during test execution and creating the bindings. In this case, we also provided it with the REST binder that is responsible to bind the REST interfaces to each other. So now that the InterACt controller is started, we can execute our unit test cases. So let's take a look at a test case of the IBAN validator. In this case, we want to ensure that when a valid IBAN is provided regarding the format, but the blacklist check fails, the IBAN validator should respond with the reason of the blacklist check. So we provide our test with a REST message, which contains the IBAN, and with the environment response that we want to use in the test case. In this test case, we want to use a response that says, okay, the blacklist check failed. We configure the mock server accordingly, and we do the request against the IBAN validator. We then assert that the body is an IBAN validation response of the invalid type, and it contains an error message that is equal to the reason of the message that we provided here as a parameter to the test case. So if we execute the test, this information will be captured in the UTBI meta model. Once we executed the test case, we can see that the information is available in the UTBI model store. We have the component, the abstract test case, the concrete test case, and the messages that were triggered during test execution, as well as the interfaces those messages were received on or sent by. Furthermore, if we refresh the view, we can see that an interaction expectation was derived from that model. In this case, we want that the IBAN that was forwarded to the blacklist checker will lead to a response that says, okay, this IBAN is blacklisted, and the reason in case of the unit test was IBAN is on blacklist. So let's execute the tests of the blacklist checker. In this case, we have two tests, one of which is testing when an IBAN is on the blacklist, it should report with a match, and the other one is when an IBAN is not on the blacklist, it should report with no match. So let's take a look at the first test case. In this case, we want that the IBAN is on the blacklist, so the actual blacklist store is provisioned with a certain state based on the message that the test case is parameterized with. In the other case, we make sure that the blacklist store is empty, so the IBAN will not be on the blacklist. After both test cases are executed, the information about the component's behavior in the two different scenarios is also stored in the database. Taking another look into the database, we can see that the blacklist checker's interfaces are bound to the interfaces of the IBAN validator component. Using this information, we also generated two interaction expectation validation plans. These are used to validate the interaction expectation we've seen before. One of these interaction expectation validation plans goes from the unit test case of the IBAN validator over the unit test case of the blacklist checker that checks that the IBAN is on the blacklist, back to the test case of the IBAN validator. And the other one goes over the test case of the blacklist checker that ensures that the IBAN is not on the blacklist. Of course, only one of those two paths satisfies the requirement of the unit test case of the IBAN validator that the IBAN is actually on the blacklist. Right now, both plans are not validated, so we have to re-execute the unit tests in order to exchange the parameters with the messages that were just captured during unit test execution of the collaborating components. So first of all, let's re-execute the test case of the blacklist checker that checks if the IBAN is not on the blacklist checker reports with no match. We can see that when we execute the test case now, we not just execute the unit test case as it was specified by the team that developed that unit test case and the component under test, but we also receive new parameters from InterACt. In this case, it contains the IBAN message here that was used in the unit test case of the IBAN validator component. We also have to re-execute the test case of the IBAN validator in order to use the response that was just triggered by this test case. we will just take a look what happens here. And we can see that in this case, the test case will fail because obviously the component response does not comply with the expectations of the scenario the unit test case has towards this interaction. So in this case, the actual interaction expectation validation plan could not validate the interaction expectation. However, we also have the other interaction expectation validation plan that we can try as a candidate. So let's do this next. So we will execute this unit test case. And this time we will also retrieve the IBAN that was used in the unit test case of the IBAN validation controller, as the other interaction expectation validation plan still provides us with that path. So as we can see, we once again see two test cases generated, one for the unit test case as it was specified by the team, and the other one with the IBAN that was specified in the unit test case of the IBAN validation controller. If we re-execute the unit test case of the IBAN validator now, we can also see that another time two test cases are generated, the unit test and the one that we got provided from InterACt. If we compare these two test cases, we will see that the actual response we now receive for the blacklist checker is different for the unit test case and the interaction test case provided by InterACt. So let's take a closer look into the unit test case execution. We see that we received the stimulus with the IBAN. We sent a component response with the IBAN to the blacklist checker, and we received an environment response that just says, okay, it's a blacklisted IBAN and the IBAN is on blacklist, that's the reason. And the unit test case is successful, obviously. We also have the interaction test case, which says that the environment response in this case is IBAN is suspicious. So the message is different, but the actual assertions that are made by the unit test case are still satisfied. And as all these test and interaction tests were successful, we will see in the database that the interaction expectation validation plan validates the interaction expectation we just derived. Of course, we could have executed all the test cases at once, but we did this step by step for demonstration purposes. So let's take a final look into the database. As you can see, all the information about the interaction test cases are also stored in the UTBI model store, and we have our interaction expectation validated. Not by this interaction expectation validation plan, but by the other one that was successful. The interaction expectation validation plan also contains the IDs of all the test cases that are needed in order to represent the interaction that was tested here. Right now, InterACt only supports specifying interaction expectations via the unit tests or deriving them from those unit tests. Not all interaction expectations are contained in unit test cases, and that's why we are currently working on some specification mechanism for interaction expectations that are not contained in unit test cases. But we plan to reuse the validation approach of InterACt as shown right now. InterACt can also validate interactions that span multiple components. As the paths are looked up every time a new model is created, it can also adapt to architectural and behavioral changes of components and systems. So if one component is split up into multiple components that have to interact with each other to fulfill the same requirement, it will just adapt the interaction test cases and still validate the integration of those components.